Hi guys, in this video we will explore how to structure your code to render arbitrary number of objects with metal. Even though I haven't made a video in a while, I still kept working on my own engine and game, and what I noticed is that a lot of the tutorials on YouTube, they will tell you how to render just a single object, like a triangle or a mesh. But when you want to make a next step and figure out how to build this pipeline so that you can render your game scene that contains many objects, then it's not really clear how to do that. So I thought I would share how I'm doing it currently in my engine. We will use this example scene that I have here. It has two meshes rendered currently, as you see. One of them is the cube and another one is just a line. But actually there is also a third element that is being rendered, and that is a setting of the background of the window, which is also in metal is treated as a separate rendering element. Before we can look at the code, we should understand conceptually how my code is set up. Essentially, I have an array of elements that I want to draw, and in my code I call that array render group. In that array I have three entries for this particular example that we are studying. I call them render entry. Each render entry, it has two parts. One part is the header and another part is the entry itself. Header just has two fields. One is type, to indicate the type of this render entry, and in our case it would be a clear entry to indicate that we just want to clear the screen. Another type would be line, and the third line would be mesh. Mesh is just a generic entry type for any 3D model. In our case, that model is of course a cube. And another field on the header is next, which is the pointer to the next entry item in the render group. Let me just draw them for completeness. So in our case we have three render entries in the render group, and each render entries it consists of two parts, right? Header and entry, let's say HE. And so this next pointer, it would point at the beginning of the header of the next entry, and so on and so forth. So you could see that basically my array, my render group, is just a linked list. Entry part, it just contains whatever data we need for rendering. In the case of, let's say, clear entry, that would be just a color that we want to set window background to. In case of line, that would be color as well as start and end vertices of the line. And in case of the mesh, that would be an array of vertices alongside their colors. And because of that, each entry element in this render group array, it will have a different size depending on how much data it contains. And because of that, we have to have this pointer in the header so that we can iterate over this array, iterate over the rendering elements in this render group. We will have to use this next pointer to do that, because each entry size can be different. There is one more point that I wanted to make. Remember how in my previous video about the memory management, I said that I will not be doing constant allocations throughout the runtime of my program. Instead, in the beginning, I will allocate large chunk of memory. In my case, I think it's 1 gigabyte. And then I will just use this allocation throughout my program to store different parts of data there. And so for this render group, what I do, I will take this allocated 1 gigabyte and I will say, hey, I will just reserve the first 256 kilobytes of this allocation to store this render group array there. And every frame, I will basically start overwriting whatever render group was stored there in the previous frame with new render group for this particular frame. And I will keep doing that over and over again, reusing the same region of memory. And I think this is very nice and elegant and efficient thing to do. Let's now look at the code. The first thing that we have is this update game and render function. That is the function that's being called every frame. And I do a lot of things here, but the one thing that we are interested in is the part where I initialize and populate the render group. So the first thing that I do, as I was saying, I will reserve this 256 kilobytes of memory in that allocated chunk for my render group arena, and I will initialize that every frame. The next thing that I would do is I would create the render group and populate that. Let's first of all take a look at what render group structure is. As you can see it here, it has a maximum push buffer size. It is the maximum size of this render group array, this one. Then we have a push buffer size. This is the current size of this render group array. Push buffer base is the pointer to the start of the array. And then also we have a number of elements stored there. In our case, that would be 3. And then this field, pointer to the previous render group header. And in this case, we talk about these headers. This is just an implementation detail that I need for my code to work out. And then the last thing that I have is, of course, the transformation matrices to go from model space to screen space, and I will use them in shader. Now let's look at the structure of each individual render entry. As I mentioned, render entry consists of 2 parts. One is the header and another is the entry itself. So header just has 2 fields, like I said. One is the type, which in my case enum, with 3 different possible types, and then also the pointer to the next header, as we saw. And then for entry, it can be of 3 different types. In my case, first is just entry clear to set a color of the background. In that case, we only have a color here. If we have a line, then it would have color as well as start and end vertices. And then another type is the generic entry mesh type, when we can use for any 3D model. In that case, it will have just a pointer to the array of vertices packed with colors and of course the array size. Now let's take a look how we populate the render group. To put every render entry into the render group, we have a separate function here. So for example, for entry clear, we will call push render entry clear and pass a color in. For the line, we call the push render entry line function and pass the color alongside the start and end vertices. And for the mesh, we will call push render entry mesh, and we'll pass an array of vertices and the size of that array. And we can look at the implementation of this push render entry functions here. They are pretty much the same. We would just do a pointer arithmetic here to set all the fields of the render entry parts accordingly and ensure that we set a pointer to next render entries and so on. For the sake of time saving, I'm not going to spend time on that. If you get access to the code, you can check it out yourself, or you can just make a screenshot of this code and explore it offline. I just want to point one important consideration is that the way we implement the drawing it's basically going to be a painter's algorithm, and the essence of this algorithm is that every subsequent render entry that we draw on screen, it will be drawn on top of the other. So for example, if I first clear the screen in, let's say, gray color, and then I want to draw a line, then of course that line will be drawn on the already gray colored screen, and then if I render a cube after the line, then the cube will be rendered on top of the already rendered line, and so on. And if that's not good enough explanation of this algorithm, then you can certainly look it up online. With that said, it's very important to ensure that the clear entry is always the first in the render group, because this clear entry will clear the entire screen into a certain color, and if it was not the first one, then it will override everything that was drawn on the screen prior to it. And that is why I have this assertion here. And then, after the render group is populated, we would do some other work, and then eventually we will go on to call this render on GPU function. And that is the function where we will do all the setup, all the metal specific setup that we need so that everything is set correctly on GPU for rendering. Here is this render on GPU function, and you see how with this one we entered the world of Objective-C and metal, because in the previous file here it is just a pure C++, there is no indication of which platform we run on. And in fact, this is actually platform-independent code that would run on every platform. And then only in this render on GPU function, it's only here that we do a platform-specific code. Let's look at the general order of events here. So the first thing that we usually do, we just would create a command buffer and we would get a drawable from the metal layer. And then after that, we would start iterating over the render group array, basically taking each of the entries in order and just setting up commands in the command buffer to render that. And then moving on to second entry, set up commands in the command buffer to render that and move to the next entry, and so on and so forth. And then eventually, after we do all that, we would call a present drawable on command buffer and then commit. And then after that, GPU will start actually doing the work. So let's see how do we actually iterate over that render group. Basically, for each entry, the first thing that we do is we look at the header type. And then, depending on what type it is, so for example, it's maybe entry clear, then well, basically for any type, we would create its own render command encoder, then encode any commands that we need to render this particular type of mesh, and then we will code end encoding after that. And as you'll notice, for any type, we do the same thing. We create render command encoder, we encode commands, and we call end encoding. It's just that the number of commands that we encode will be different depending on different entry types. So for example, the simplest case is this entry clear. We don't have any vertices at all, and all we do is we just set a color attachment clear color, and that's all we do. However, for example, for render entry line, we do a lot more things. Now that we have vertices to draw as well, we have to have shaders to render them. And because of that, we also, in addition to just render command encoder, we have to create the render pipeline descriptor and set up a depth attachment and also create depth stencil descriptor. And if you are unfamiliar with this type of pipeline, then you could go watch my video on how to render 3D cube. From some time ago, there I go into more detail about each of those things that I just mentioned. And so eventually, after we set all those things up, we, as usual, create this render command encoder, set vertices to buffers to be sent to GPU, send transformation matrices as well, and then we just make a draw call specifying the type of the primitive that we will be drawing, and then we call end encoding as well. And for the render entry mesh, we basically execute exactly the same code as we do for the line, specifying shaders and all that, and passing vertices to GPU and calling end encoding in the end again. There is actually a number of potential pitfalls that you must be aware of. So one thing is that, remember I said that we are implementing the painters algorithm where each subsequent render entry will be drawn on top of whatever was drawn previously. And in order to achieve that, we actually must correctly set this load action on the both color and depth attachment actually. So for example, for color attachment, for the clear entry, I specified the type as MTL load action clear, which means that I want to reset the entire color texture to be of a specific color, and that's the first thing that I do. But then, for example, for subsequent render entries, as you'll see, for color attachment, I use a different type of action, which is load action load actually, and it's very important to use that because this action ensures that we will actually retrieve the texture with everything that we drawn there previously, and we will be drawing on top of that. In order to retrieve this texture and not reset it, we have to use this load action load action. And for depth attachment, I think we will need to do the same thing. I use a load action clear here, but I think it's incorrect. We should be using the load action load everywhere. Well, in this case I use clear because this will be the first time that we create the depth attachment, I think. Anyway, I will have to clean this up, but hopefully you got the idea. There is another area of improvement in my code. Currently, like I said, this code to set up GPU for render entry line and render entry mesh, it's actually exactly the same, but it is very inefficient because this method that I am executing, render on GPU, it will be called every frame, and basically every frame we just have about 60 milliseconds to do all the work that we need. And this code that I have here, it's inefficient because it is creating the render pipeline state from scratch and depth stencil state from scratch, and it also allocates memory for the buffer here as well, and it is all not a good practice. It's not recommended to do that in every frame. Instead, it's recommended to do all the setup during the initialization when your application just starts. And we can actually do that potentially, because one conceptual thing that it's very good to understand about Metal is that, for example, the depth stencil state is the thing that you will probably reuse across all shaders that you have. At least that's my current understanding. So I think it's very simple to just create that once at the initialization and reuse it everywhere. And another thing is the render pipeline state that we might want to reuse. And what you need to understand is that render pipeline state, it's simply a way to say which pair of vertex and fragment shaders you want to use to render a particular mesh. And so, for example, in my case, I just have one pair of vertex and fragment shaders, and I use them for both line and the cube. And so, because of that, what I could have done, I can just create a render pipeline state on the initialization for just these two shaders, and then on the render on GPU function, which is called every frame, I don't need to create it again. I just need to say, hey, just use that pipeline state that's already created during initialization, and that will be efficient. Just one thing to figure out is which buffer to use, right? Because maybe you can't really reuse the same buffer for the same pipeline state, or maybe you can. It's kind of the question that I haven't still figured out myself, so that I will look into that and maybe I'll report it in the future videos. But for now, what I do, I will just basically every frame I will just allocate all the memory for all the GPU buffers, this pipeline state, depth stencil state, and I will just basically release them at the end of the frame. So I think it needs to be cleaned up, and I will probably do that in the future. If you made it this long into the video, I assume that you like my content, and now there is an option to support my channel. I just opened my Patreon here, and currently I have two options. If you just want to have more videos and better explanations and better quality, then consider becoming a supporter. But if you're also interested in working on your own game engines, then consider joining the premium support options, where not only you will support my channel, but you will also get access to the full source code for my engine. And as I mentioned, I've been working on this engine offline for many months now, even though I haven't posted videos about it. So there is a lot of code in different areas, particularly in the macOS platform layer, where I use the lowest possible APIs for things like audio input processing and video handling and all that. So you can check all that out if you get access to the code, and just if you want to explore the code more and kind of better understand what I am explaining in the video, then you can join and see the code for yourself. And also I keep making commits all the time, and you will have access to the code and you will see all the commits that I make as well. So you will basically stay on top of the latest changes if that's of interest to you, and that way you will not have to wait for me to release a video to report on any changes that I did in the past. And that will of course greatly support me and give me motivation to make more and more videos about my engine and my game. But that's all for today. Thanks a lot for watching, and hopefully I will see you soon.